Have you ever wondered what the actual rulebook for the universe looks like? Well, it has a name: thermodynamics. Seriously, this is the science that explains pretty much everything, from how your car engine works to why the sun shines. And we're about to break down the most important rules.
Okay, think about this for a second. If you rub your hands together, you're doing work, right? And what happens? They get warm. You're creating heat. Super easy. But what about going the other way? How do you take that messy, random energy of heat and turn it into something useful, like organized work that can power a steam engine? That question is the absolute heart of thermodynamics, and figuring it out literally changed the world.
So, before we can get into the rules, we first need to understand the playing field. What are we even talking about here? Let's get that big picture view.
Here's the first thing you gotta get. Thermodynamics doesn't care about every single tiny atom or molecule. I mean, trying to track all of them would be completely impossible. Instead, it looks at the whole forest, not the individual trees. It deals with the big stuff we can actually measure, things like pressure, volume, and temperature.
And to even talk about that forest, we need one key piece of lingo: a system. And don't worry, it's simple. A system is just whatever part of the universe we decide to focus on. It could be the gas inside an engine, a cup of coffee sitting on your desk, or shoot, even an entire planet. It's just our area of interest.
All right, so we've got our playing field, the system. Now let's meet the three main players that are always interacting on that field. We're talking about heat, work, and energy.
The players have names, of course. There's internal energy, which we call U, heat, which we call Q, and work, which is W. And right away, this lets us bust a huge myth. You probably hear people say something has a lot of heat. Well, technically, that's wrong. A system has internal energy. That's the grand total of all the energy of its molecules bouncing around. Heat, on the other hand, isn't something you possess. It's what happens when energy is on the move.
The easiest way to remember this is a system has internal energy. That's what it owns. It's like the balance in your bank account. But a system does heat and work. Those are actions. They're the transfers of energy, like making a deposit or spending your money.
Now that we know the players, we're ready for the first rule of the game, and this one's a biggie: the first law of thermodynamics. You might know it as the law of conservation of energy, but I like to call it the no free lunch rule.
So check this out. When you add heat, that's Q, to a system like the gas in the cylinder, that energy can't just disappear. It has to go somewhere, right? It can do one of two things. It can either increase the internal energy of the gas, which just means making its molecules move faster, or it can be used to do work, like pushing this piston.
It really is just like your bank account. The heat you add, Q, is your income. That money either goes into your savings, which is the change in internal energy, U, or you spend it, which is the work done, W. Just like money, you have to account for all of it. Energy is conserved. You can't just make it up out of thin air.
Okay, so if the first law says energy is always accounted for, the second law is the one that tells us which way things naturally want to go. It basically gives a direction to time itself.
And honestly, you already know this law just from living your life. A hot cup of coffee is always going to cool down, right? It gives its heat away to the colder air around it. Heat always flows from hot to cold. You will never see a lukewarm cup of coffee suddenly start boiling by sucking heat out of the cool air. The second law says that's just not how the universe works.
This whole one-way street thing is why we call the second law the arrow of time. In the real world, things are irreversible. A shattered vase doesn't magically put itself back together. The universe naturally moves toward more and more disorder, a concept we call entropy. And it's not just vases, it's what happens to everything. The only processes that are perfectly reversible are just ideas, these theoretical ideals, like a pendulum with no friction that could just swing back and forth forever.
So what do these rules actually mean for us? When we're trying to build things like engines to do work? Well, it turns out they set a very, very hard limit on what's even possible.
Physicists, being clever, came up with a thought experiment to figure out the absolute best you could ever do. It's called the Carnot engine. Now, this isn't a real machine you can buy. It's a perfect theoretical engine that only uses those ideal, reversible processes we just talked about. This thing represents the most efficient engine that the laws of physics will ever allow.
But, and this is a huge but, there's a catch. To squeeze every last drop of energy out of this perfect engine and get 100% efficiency, the part of the engine that gets rid of waste heat, what we call the cold reservoir, would have to be at the coldest temperature physically possible in the universe, absolute zero.
And just how cold is that? It's minus 273.15 degrees Celsius. That is the ultimate cold. And while we can get ridiculously close in labs, we can never, ever actually reach it. And so, a 100% efficient engine is physically impossible. Period.
So let's just quickly recap. First, a system has internal energy. It does heat. Second, the first law says there's no such thing as a free lunch. Energy is always conserved. And third, the second law says things only go one way, from hot to cold, which means a perfect 100% efficient machine is impossible. These aren't just rules for engines, folks. These are the rules of the game for the entire universe.
And that leaves us with a pretty fascinating question, doesn't it? The laws of physics have drawn a line in the sand. We know perfection is impossible. So knowing that, what's the next great frontier for us as we try to get smarter and smarter about harnessing all the energy that's around us?